Ooh,
That
that was hard.
That's always fun.
Yeah.
The bold choice in sweatshirt, dude.
Nice.
It could have been worse, and I've
Could have
seen
been
what.
worse.
Oh, I have one in mind that I have seen. That one.
Whatever it's called.
Yeah.
I have two of those.
Okay. Yeah. All right. Fluids and all.
Have you guys watched that new anime Chainsaw Man yet?
No, but I've heard of it.
Seen bits and pieces of it here.
This is pretty good. I like it.
I watched the first episode of that Cyberpunk anime finally.
Oh, that's actually pretty good.
That problem.
That's actually a pretty good.
Well, yeah, I was
Series.
immediately sold on the fact that like the theme song is from one of my favorite albums. So right away I was like, okay, this is gold.
It's a pretty good series, actually. Hope they make another one. So
Yeah, I will. I mean, it managed to get the amount of players on the game to be decently high, so yeah, it'll probably get another one. Well, then again, it's on Netflix and they're idiots. So. Oh, Netflix, what's that? You have something successful? Cool, cancel it. Every freaking time.
you say
They make on and off shows.
I don't even try to watch Netflix original series until they hit season 3, so I know I actually have something to watch.
The Dark Crystal series was pretty good.
Was it? Oh yeah, I heard about that. And then it got canceled after season 1. There's my problem. Stop canceling your stuff. I was loving Santa Clarita Diet. It's beautiful, absolutely beautiful. And then they canceled it after season 3. Like, no, you can't do that. This clearly has an ending and planned.
it's funny how that is though. They don't get enough views gone. You know, it's like
Apparently they judge it based on like the weekend that it drops. So like, I guess they aim for having the most amount of people who have completed the series by the end of that weekend. And the higher that number is, the more of a shot that they're actually gonna renew it. So even if it's like a slow burn and gets popular, they don't care. It didn't hit their algorithm the right way.
so waiting for Breaking One Punch, man. For the new season to come out.
Watch like 3 episodes of that. I need to get back.
I love it. I love the comedy on it. It's pretty funny.
It's gotten really.
Yeah, I wish they would show the stuff that they. I found like a Japanese website, but man, I don't read Japanese. So it's like, oh man, look at all these shows.
I don't know what that sound is because everybody's muted. So that's probably on my end. And I don't have anything saying that it's getting plugged in and unplugged. So that's cool. I have a question in the chat. How's my back? Oh, it sucks, but it's better than yesterday, which is better than the day before. So I was actually saying that this is going to be the longest today that I've stood up without having to go to something to like lean my back against it or have a heating pad or ice pack or whatever. So we're going to see how long I get through it. I took some Excedrin. I got this. I am old. I am cranky. I will continue to break my back doing stupid things. This time I'll actually let it heal before I do something stupid. So how long does it take your back to heal?
Depends on you.
Well,
I have
the number wasn't a week. I can tell you that.
depends on you.
Oh man.
I have an inversion table, so that helps a lot. That happens.
I don't know what that means.
An inversion table?
Yeah.
Oh, the one you hang upside down. Just that. all your back decompressed. If you can do that,
That sounds awesome.
you know what I mean? If you can do that, then that's perfect.
Pull up a chair and sit down. Well, I don't know. Yeah, you've been in this classroom. The chairs are all short and the desk is tall, so I don't know if you can see my webcam right now. But if I sit in the chair, you still see my head, but nah, that doesn't work actually. Something cracked. Wasn't where I wanted it to be. It was too high, but it was still nice. Lower back pain's the best back pain. And yes, I'm absolutely intentionally wasting time to see if I could get more than 3 people on the Zoom. Oh. Yeah, I don't know why that TV's off. I think they both use the same remote. Uh-oh.
Yeah, they do.
Oh, Jesus. Okay, I see this problem happening. Okay. Somehow,
Someone messed up.
uh-huh.
Wait, there you go.
There we go. I got both TVs on at once. Did I need to? No. Cool. All right. That was mostly pointless. Breathe for a second. Gotta collect my thoughts. Haven't taught you guys anything in like a week. Gotta be not useless. This time I actually, well, 2 days late, I remembered to submit my timesheet because I actually haven't been paid for this in like this entire class. I haven't gotten paid a cent because I completely forgot the last pay period. I'm god awful with that. Whatever, I don't care. It's basically like a hobby. You ever teach a math class as a hobby? No.
Not fast. So what's the other schedule after the 21st? I know this one will end on the 21st, right?
Something like that.
And
I
then-
think it actually just, I think it's a little while until the next one. I'm not honestly sure.
I know, because I know this December break, I know that. And then
Yeah,
January, I'm assuming.
something in
spring.
January. I don't know, but the next one's gonna be, the next class is gonna be 8 weeks long, not 2 6 weeks. Because apparently, I'm assuming that didn't work for anybody. So chances are, this is the only time I'm gonna get to cover this particular class. It felt bad. This took me like 3 hours to type on, no, 4 hours to type this out on Monday. And then I just didn't get to go over it. So I was like, shit. So, yeah. Tonight's all, no, almost all polynomials. We're gonna have some fun with that. Gonna do the review as usual, functions and fractional exponents. That's been long enough to the point that the review is probably gonna come in. So, functions. Covered functions last time. Functions are special equations that relate an input to an output. Every function has only one output for every input. So you put a thing in, it spits out one number, not 2 numbers, not 5 numbers, spits out one number. Every function is an equation, not every equation is a function. So for practical purposes, think of this as an equation where every x value has only one y value. So a circle wouldn't count as a function. You can make an equation that's a circle, but it's not a function because on every x value on a circle, well, there's 2 y values that it has on those x values, right? Because, you know, circle covers things twice. It's great. So in a function, the inputs are called the domain and the outputs are called the range. And I guess I shouldn't actually, I'm gonna drop the words in a function because that's just a general thing for every equation. The inputs are always the domain, the outputs are always the range. So x's are always domain, y values are always range. So function notation. Function notation has function names. Then it has whatever your input variable is in the parentheses. So usually you'll have f of x. Sometimes you'll have g of x. Sometimes you'll have h of x. Sometimes you'll have q of x. I don't even care. You usually just name it for whatever it is. So like my go-to example is usually revenue, cost and profit. You usually have a r of x, c of x, and p of x. You just name it whatever the heck it is, and it makes your life easier. So f of x basically takes the spot of y equals. So every one of them can be graphed that way, no problem. But you have separate functions because they're for different things, right? And yeah, sometimes the functions just don't have a name. You have y equals x squared, but that still means that you have one thing being the input, the relationship between the input and the output, and it spits out one output. So any equation that spits out one thing for any x value makes it a function. Doesn't have to have a function name. So there's two rules that they cover. So it has to work for every possible input, and it only has one relationship for each input. So basically that just means, yeah, everything you plug in is going to have one output, period. You can't randomly say, oh, okay, well, it kind of works over here, but not over here. No, whole freaking thing. You plug something in, you get one output, cool, function. More on that. One to many is not allowed, but many to one is allowed. So that means, I mean, easiest way to think about it is think of a wave. It's going like this. Every input, every x value has its own y value. And you can hit that same y value multiple times as x goes further on. You keep hitting that same height, and that's fine. You can get away with that. But you can't have it circle back on itself and have more than one output. So that's why one to many is not allowed, but many to one is allowed. And like I have down there, that's basically just relating domain to range. One thing in the domain can't have many in the range. So graphically, this is useful because I have no examples for this one on this particular slideshow. But graphically, easiest way to tell if something's a function is to see if it passes the vertical line test. Usually that involves me using my pen and just kind of like scanning across the graph. If it crosses any vertical line more than once, it's not a function. Please slide your chairs under the, I just now noticed that somebody actually put up a sign to push your chairs in. This place must have been a horrible mess for that to happen. And also one chair is against the wall, and I find that hysterical. It's like a massive act of defiance. Yeah, so on the right there, that one's not a function because, yeah, to the left of that S curve happening, it works. To the right of it, it works, but in the middle, everything blows up. If that happens at all, not a function. And domain and range. This one's useful for every equation, not just functions. But you'll see the terms domain and range pop up more often as you take further math classes. So domain is always the x values of an equation. Range is always the y values of the equation. And I mean, yeah, that's pretty much it. I always just kind of like mentally squish the graphs in a certain direction to kind of be able to see it a little better. I think I can actually get away with doing I gotta freak it out. Oh my God, that did not work out as I was hoping. Control Z, undo. That is what I live my life by. Yeah, but I just kind of like mentally like squish it. Like if I'm looking at the Y values here, I don't care that it travels over the X values at all. I just care, okay, lowest point to highest point. Domain, furthest left to furthest right. That's how it always works out. You always go low values to high values, and you're only caring about one axis at a time, and then you're peachy. Examples. I love examples. So do you guys, you just don't know it. So first three, I have just for this one function. Don't need to know it now, but this is a parabola. It's going to be like a U shape. I don't know where the U shape is. It's not in the proper format for me to be able to eyeball it. Which is fine, because I don't have to. Decent at math, I'm not that decent. So you can see the function notation coming into play on how the problems themselves are. That'll kind of work. Okay. So for this equation, we are defined all three of these things. So the first two, function notation wise, if you look at this, our function name is f, our variable is x, and then we have a bunch of stuff that's basically giving you the relationship between that input x and whatever the output would be, which would be the function value. If you're graphing this, you can call it y at this point. That's fine. You could treat this almost like a y equals. That's what I do because, you know, whatever. But what's happening here is you could see, oh, this is my function name, and that's the variable. So if I have f of 2, that's asking, hey, where's the function where my variable is a 2? What does that look like? Well, it looks like this thing with a bunch of 2's in it instead of x's. So I'll rewrite that thing, but wherever I have an x, I'm going to put a parentheses and pop in a 2 instead. So it's an easy way to say, hey, x is 2, what's y? Pretty much. And if it helps, you can write that below. In fact, until you want that, if you're still a little hazy on these guys, I recommend that. That comes in handy. That's how I usually teach it. You do 100 of these, you don't have to write that anymore because it makes sense to you. Until then, nothing really makes sense. You're just rolling off of repetition and copying what's in your notes. So you just kind of move with the punches. Okay, well, all we have to do is figure out what that is. So one of the things I'm going to cover is the fact that this is a polynomial already. So terms are usually separated by pluses and minuses. So for each of these terms, we could clean up a little bit, right? Like we don't have to just do one thing at a time. I can look at this 5 times 2 squared and say, hey, that's a 5 times 4, right? Minus, well, I can do this right now, right away too. 2 times 2, that's another 4. advanced ways of doing algebra. I can look at this and say, hey, I got 5 4s. I'm taking away 1 4. That means I'll have 4 4s. This thing is going to be a 16. If you can't do that, that's fine. I usually scramble people's brains by doing that. But we have 5 times 4, 20 minus 4 plus 3. So 20 minus 4 is 16. 16 plus 3, 19. And based upon some of our properties, we could just say minus 4 plus 3. We could combine those to a minus 1. And then you would have 20 minus 1. You can do that too. Doesn't matter. All right, so we have f of -3 as the next one. I'm gonna box this, or I remember sometimes, don't remember all the time. So we do the exact same thing. Plug in the -3. But we do have to be very careful about that -3 because of the sign. That's another reason why I usually do this as sets of parentheses instead of just saying, oh, this is -2 times 2. I could do that. It would technically mean the same thing, but if I have a negative in there, I might screw up my signs. So as long as I put these in parentheses, I'm usually pretty safe from doing that. So that's why I use the parentheses most of the time. So something like this, the first thing I'm going to do is square that -3. -3 times a -3. Negative times a negative is a positive. 3 times 3 is a 9. So we still have a 9 in parentheses there, and that's still multiplied by 5. Over here, this is where it comes in handy. Now, there's a couple of ways to look at this. Might not confuse some of you it might, but -2 times a -3 is still, this is still a negative value, right? That -2. So you essentially have a negative times a negative, which gives us a positive, and then 2 times 3 is 6. So it's negating that negative happening here. It's one of the things I like to go over when I do like order of operations. The reason addition and subtraction are on the same level is because adding a negative is the same as subtracting. It's just cutting out one of the symbols and makes it make a little bit more sense. Okay. And we still have that +3 hanging out at the end. Okay, so what I'm going to do on this one, I can multiply these guys. 5 times 9, that's 45. But I can also just add these guys right away, right? These guys will go together, no problem. So 45 plus 9, we end up with 54. Okay. And then the next one was asking for the x value for f of x is equal to 3. So I wrote that out quite nicely to be able to understand it. But anytime you see your function equals to a number, that's basically telling you, hey, that would be if I had the y and I was looking for the x. So kind of the inverse of what we had up here. This one gave us the x and we needed to find the y. Now it gave us the y and we need to find the x. Now, thinking I picked the wrong value. Hold on a sec. Do not have the skills to do this fancy right now. Oh. absolutely have totally the wrong thing. I picked this 5x squared minus 2x plus 3. At random, as I often do. However, this totally doesn't work for what I was trying to shoot for. So here's the problem that I just realized I backed myself into a corner about, because I was hoping that I could break this down to the point that these values would just kind of drop off. But I kind of broke math a little bit. Didn't necessarily broke math, not break math, but I totally broke what I was thinking at the time. We do not have the skills to solve this right now. 3 equals 5x squared minus 2x plus 3. We do not have the skills to solve that at this point. I was hoping that I was going to pull off something that was going to work out nicely, but
Can you show the steps anyways?
I can, I see what I was shooting for.
Yeah.
And we can actually find one of the values. But this answer would actually have 2 answers. See, I'm getting ahead of myself by about a week by explaining this, okay? But if I have an x squared, that means I'm going to have 2 answers for x. That's what that means. So if I had an x cubed, I would have 3. If I had an x to the 4th, I would have 4. And that's how it usually works out. Sometimes you'll have the same x and it'll repeat. Don't worry about that yet. It happens. But my problem here is that the way that I have this structured, we can find one of these answers quite easily, but we can't find the other one easily. And I am not going to go into how to find the second one at all, because I don't think that's going to be something that you hit at any level for the HSE or the GED. But finding the first answer is quite easy, because 3 equals bunch of stuff with variables plus 3. What is x going to be to make that true? Well, this is a 3 and that's a 3. So the only way this would work for me finding one of my answers is if all of this stuff was 0, right? Like if that didn't exist and that didn't exist, then we'd be peachy. Well, the nice thing is there's multiplication happening here. So where would this all disappear when x is 0? That would give us 5 times nothing squared minus 2 times nothing plus 3, right? So I'd get 3 equals 3 and it would check out. That would be one of my answers. Now, in order to actually solve this, well, I'll write down what it is, and I'll leave you, if you're curious enough, to explore a couple of YouTube videos. But I'd recommend, if you wanted to explore that, wait until next Tuesday's lesson. I think that's going to be when I cover that. And it would be the AC method of factoring. Because today we're just going to be covering. Today we're just going to be covering polynomials. Next time we're going to be, hey, this is what we can do with some of those, right? So that'll be fun. There's all kinds of rules for that, and they're not too bad, but if you get them down, you look like a freaking ninja, and it's great. But yeah, it would involve multiplying these two numbers together. Factoring by grouping is another concept that it would need. And you get both of those concepts down, and this is an easy problem. Now, if you don't get those concepts down, well, how would I do that? Just be lazy and pull out a graphing calculator or something with a graph, figure out where y is 3, and just try to eyeball it. Just keep zooming in on that sucker. This is 100% what I did on some tests. I'm not gonna lie. I would graph something in my calculator and be like, let's get that to 0. It's about there. So I'm betting about 4/10 would be the answer. So 2/5. Is that cheap? Well, yes, the answer is in fact 2/5. The other answer is 2/5. So being cheap and graphing it and then zooming in really close and eyeballing it kind of works sometimes. Totally, like if you're in a pinch, that is something I've done and it works. Yeah, because if I keep zooming, it gets closer and closer to that 0.4. So as it gets closer, you just be like, chop all that off, convert it to a fraction, and then reduce it. You end up with 2/5. It's terrible to teach that to you guys, but it works. It's a horrible shortcut. There we go. Cool. Yeah, so don't stress the other answer. The other answer is 2/5. I'm just gonna have that kind of off to the side. But we got one of them analytical. We just kind of work our way through that logically. And that's fine. That's peachy. When I wrote that question, I didn't stop to think, oh yeah, there's going to be 2 answers for that. If I had put the vertex on the axis, then there would have been 1 answer, and then we would have been golden. But I didn't, and that's my fault. My bad. Yeah. Well, now that I pulled that, let's look at more and see if I made any other horrible mistakes of, oh my God, what do I do now? So I got a bunch of these guys. Nice thing is that number 2 and number 3 are going to be things we can eyeball. In fact, number 4 is kind of one we can eyeball, but having a graph might come in handy. But number 1, that seems like something we want to do. I just wanted to have a problem like this in case you're on a test and you're like, oh God, what do I do when it's like this? Well, you do the same thing. If you are given some weird, horrible function and it's like evaluate for this, that's no problem because you do the exact same thing that we did on the last one. If I'm looking for f of 3, that just means I'm plugging in a 3. I have 3 times 3 over 3 minus 4. Okay. So 3 times 3, 9 over 3 minus 4, -1. So what do I get if I get a 9 over a -1? we get a -9. Because a positive divided by a negative is a negative regardless, and 9/1 is just 9. Pausing for notes. Checking my notifications while that's happening. Now, like I said, number 2 and number 3, we can just pull off by eyeball. Because in that case, don't be terrified by the set builder notation. That's what that's called, is set builder. That's where you use a little curly braces and you just have things separated by commas. Whenever you have that, that basically just saying, yeah, we got a set of stuff. That's it. That's all that means. So determine if this set is a function is basically saying, hey, we got 4 points. Are these four points, do they fit the definition of a function? And pretty much all we have to do is make sure that each thing in the domain has only one thing in the range. Now you might look at this and say, well, yeah, we got a bunch of separate points, so we're good, right? No, we have to make sure that each thing in the domain, like that -2 right there, that -2 has a y value of 8, and then later on, we have a -2 and a 6. So that's telling us that we have the x value -2, and it has 2 y values. Well, we can't have that, right? That breaks it. That would not fit the vertical line test. And that's something you can do if you run into something like this on a test, and you're like, how can I do this without graphing these points? Remember what the vertical line test is telling you. Can't have more than one y on any given x. So right there with those -2 points, that breaks number 2, right? Completely breaks it, so it's not a function. Number 3, well, you can kind of guess that what we're doing is we're looking for repeats, right? We get repeats in the x and the world blows up. This one has a couple of repeats on the y. Can we do that? Yeah, we can get away with that because those are different x values. They still have one y value, just happens to be the same, and that's fine. As long as each x value only has one y value, you're good. But it can have whatever y value it needs to, doesn't matter. As long as it doesn't have 2. Okay, so number 3 is a function for that reason. Now number 4, here's an easy way to be able to tell. Okay, so I'm probably going to graph it. Just to cover our bases. Going to slope and intercept this graph. That makes life easier. So random axis. The y-intercept is a -2. There's our first point. Our slope is 3, so it's 3/1, essentially. So that means we rise 3, we run 1. So go up 3. Yes, this is the cheapest graph ever. Run 1. Do that as many times as we need to. Got a couple of points. There we go. Is that going to pass the vertical line test? Yeah, right? pass a vertical line through any point and graph will only cover once, right? Well, the easy way to do this problem is to notice that, well, we just have one x, right? We don't have an x squared, we don't have an x cubed. So what ends up happening is, as long as this isn't a vertical line, it's a straight line, right? Something like this is always going to produce a straight line. As long as that straight line is not perfectly up and down, as long as it's sloping one way or another way, as long as it's not straight up and down, it's going to work as a function. Every straight line is going to, unless it's a vertical line. Because that's the only time it wouldn't pass a vertical line test, is if you have a vertical line. So, yes, it's a function. My U looks more like an N than my N does. I have failed. This is why I do math, not English. I always like to say English is a stupid language anyway. It's just a mashup of other languages. There's no logic there. It's just a bunch of crap all thrown together. Keep playing it. Okay, do we feel good on functions? Do we need to see more? Do I need to pull magical functions out of my hat? Or are we feeling okay? Pausing to see if anybody actually says anything. Don't think anybody's going to say anything. Moving along. Fractional exponents. That bottom thingy there, that bottom thingy is what you need to memorize. You memorize that thingy, you're probably good. Stare at it. Remember it. Embrace it. Honestly, if you remember what an exponent is, you're halfway there, right? Because if I had x squared, that means I have x multiplied by itself twice. Well, if I had x to the 2/3, that means I would have two x's multiplied together, but that denominator, that fraction denominator there, is going to give you the root. That's the difference. So if I had x to the 2/3, cool. That means I would have x squared under a little root with a 3 on the outside, right? The 3's kind of hanging out in that little, the little shrug area. I don't know what to call it. It's a radical symbol. That's what it is. There's been several times where I've tried to Google the name of a fancy mathematical symbol, like in calculus, there's this kind of squiggle thing, and it looks like a very tall S, tall skinny S, and you use it when you're doing something called integrating. And I was like, this has got to have some fancy name, right? So I Google it, try to hunt it down. Literally called an integration symbol. So I always go back to the what I like to say, mathematicians have no imagination. It's all called what it is. It's all called what it is, or it's named after the weird Greek guy that made it up. So, one thing I will say is that all of the rules on this particular slide are also incredibly important, and you should memorize all of these as well. Now, I don't care if you write them down as A and B, because that might confuse you, but if you swap them out for numbers and it doesn't confuse you, that's peachy. You can do that, no problem. I know that when I started playing around with algebra stuff, I got really confused when I was looking at all these things, like, but I'm doing numbers and now it's all letters, the whole thing. It just like that top left one, it's just saying, hey, if I got a thing to a power multiplied by the same thing to a different power, I can just add those powers together, right? Or if I have the original thing, if I have a thing to a power and it's divided by that same thing to a different power, then you do the top one minus the bottom one. Then notice that the top two equations are dealing with having the same base but different exponents. And the bottom two are dealing with having different bases but the same exponent. Now, personally, I think the bottom two would be more useful if you wrote them kind of backwards, like the right side is the left side and the left side is the right side. Because for the most part, that's what you're going to be doing. If I looked at the bottom left one and I said, hey, I have, starting with the right side, if I have A times B hanging out in a set of parentheses and it has a power on the outside, the rule is I'm going to take that power and I'm going to distribute it to each thing inside. You end up with the left side, A to the n, B to the n. Now, laid out this way, it's almost like a preview of a week from now. That's you would be factoring out the power and saying, hey, if both of these things have the same power, I could just say, I got these things with that power. It's cheap, but it works. But that's basically what's happening there. And we are going to use these more in this particular lesson. Fractional exponents. Look at all those problems. Isn't it beautiful? Love practice problems. So a lot of times problems like these will be given to you in very confusing terms, right? Like if you notice, number one is saying, hey, what is this? Number two is saying simplify. But 90% of the time, what you're going to do is get it out of the fractional exponent and try to clean it up. That's really what most of this ends up being. Get it out of the fractional exponent, try to clean it up. Because they're fine. 27 to the 4/3 is a number. That's fine, but it's kind of weird to try to visualize it, right? So you just don't. You fix it into a way that you can look at it and understand it, and then you make it a little easier that way. But number 4, I'm probably going to use a lot of space. So I'm not going to write number 5 down yet. But number 4 very much resembles when I learned this stuff originally. This would be that, you're doing math homework and they always save this one weird one for the end. And you're like, what the hell do we do? And everybody's like, oh, let's bug the teacher because I don't know what to do. And it's always got to be some weird conceptual thing. But the concept there does come in handy. So let's do a bunch of them. I'm gonna do the first couple, and then maybe number 4 will make a little bit more sense of that one. So number 1, it said, what is 4 to the 3/2? And we're just going to get a solid number out of this, but for the most part, you don't necessarily have to look at these and be like, oh God, what do I do? What do I do? How do I approach this? Because for the most part, getting it out of the fractional exponent you'll just kind of, as you're cleaning it up, it'll fall into what you're aiming for, right? So if I looked at this, I would say, okay, well, the 3 would be the power and the 2 would be the root, right? Because the top is always the power, the bottom is the root. Now, if I have my root as 2, then it's just a square root symbol, right? We don't need to put the 2 there. I mean, you can if you want to, but we don't need to put the 2 there because it's kind of the default, right? And you would have 4 cubed. Well, that's kind of hideous. I don't want to have to cube that and then try to break it down. But there's a nice thing with these that I didn't have in the slides. Because this is actually equivalent to the same thing if you put the power on the outside. You can put that power on the inside or the outside, and it actually works out the same. Now, why is that useful here? Well, what's the square root of 4? 2. So all we have is a 2 cubed. 2 times 2 times 2, 8. I just kind of like moved a little bit and it felt like at least 5 tiny little crunches in my back. Shouldn't mess with my back. Should have let that heal. All right. Now we have 27 to the 4/3. Now, the question itself said simplify. You're going to see simplify a lot. Simplify is literally, hey, this is ugly, try to clean it up. Like try to break it down, try to make it smaller, but usually it just means manipulate this into a nicer way and see what you can chop out. So for the most part, simplify is just going to be clean it up a little bit. So we're going to do the same thing. This is going to be the cube root of 27, and I'm going to put that 4 on the outside, right? Because obviously I don't want to do 27 times itself 4 times. That's just going to suck. Wow, that noise is really distracting. I wonder if that's how they feel about me. Do they have like the Peanuts parents over there? Like, right? Where'd you see their?
So on the first one, what happened to the, actually to the root? Oh, you actually with a 2, that
Yeah.
became the 2 to the 3, okay.
Yeah, because it could be a
Yeah,
square.
yeah, there you go.
Yeah. Writing kind of small, so you probably zoom. I don't know what you know, you take these classes, they tell you that, well, if you're attaching it on Zoom, you must be on a laptop or a computer. I'm not gonna pretend some people aren't connecting on their phones. So I don't want that to be too small. If I am doing something too small, let me know. I will zoom in on that sucker or write bigger. Care if you're on a phone as long as you're paying attention. I'm gonna close the door real quick. It sounds like the Peanuts parents. How was I talking about? Oh yeah. That thing. Cool. Well, we have a cube root of 27. If you don't know that right away, you could make a tree diagram. Yeah, I like those trees. 27 is 3 times 9. 9 is 3 times 3. Hey, what do I have a cube of in here? I have 3 of that 3, which means this is 3 to the 4th power. So 3 times 3 times 3 times 3 What is that? Kind of awkward to visualize. So sometimes if I'm doing these and I don't want to break out my calculator, show you a cheap way of dealing with that. See if you can break that down into something that you know. Well, yeah, it's 9 times 9. 81. So 27 to the 4/3 is 81. 4/3 of the power of 27. Weird to visualize. It works, but it's confusing. You don't overthink it. You just get it into the radical, clean it up, make it not stupid looking, and you're good, right? Like number 3 here. Like, oh God, what is happening here? What am I gonna do with this? Well, when I do anything with negative exponents, my first impulse always, before I try to play with them, is make them positive. How do I make them positive? You flip them to the other side of a fraction bar. I say that specifically because most math books will tell you, oh, it goes down into the denominator. That's all well and good, but what if I have a negative exponent in the bottom, right? Well, it actually goes to the top and becomes positive. So I like to explain it as you flip it to the other side of the fraction bar, because that explanation works for wherever the hell your negative exponent is. You'll just jump to the other side on a fraction. Problem solved, right? Well, now we have this. Well, that part's easy. I know what 4 squared is, right? That's 1/16. Am I gonna run out of room? Oh, you bet I am. But over here, I have the 4th power of 16, which is the 4th root of 16. So skipping the fact that, I don't really have enough room for a tree diagram there. What multiplied by itself 4 times is going to give you a 16? 2. I'm actually going to bring this up a little bit. So we'll have 1/2 plus 1/16. Now we just got to combine those 2 fractions. I know you guys love fractions. I wasn't going to leave them out. Everybody loves fractions. So I got to get, if I'm adding 2 fractions together, I have to get a common denominator. So the common denominator between 2 and 16 is going to be 16, right? Because 2 could go into 16 how many times? 8 times. So I'm going to multiply that thing. Yes, I know this is hideous and I drew it over my arrow. I don't care. I'm going to multiply that thing by 8/8, because 8 divided by 8 is 1, and I can multiply anything by 1. So I have 8/16 plus 1/16. Well, that's easier. So I have 9/16, right? Cool. That's as good as we're going to get. So quite a few steps. Step 1, we've made everything have positive exponents. Always a good first step. I don't like to mess with anything when it still has a negative exponent, because I am very likely to mess that up. Very likely. So the first thing I always do before I even try to manipulate anything, I always make all my powers positive. Then I can start messing with it, right? That's where I converted. This guy was easier. And then we just had 2 fractions to add together. Common denominators abound. Are we happy with this? Well, I guess we're not happy with it. Are we content? Are we good with it? Do we hate ourselves less? That's a trick question. The answer is, I don't know, maybe a little bit. The meds is working today. The meds is working. The crazy pills are downsizing the crazy. We are happy. We are happy until we see number 4, and then we're like, what the hell is that thing? We have the third root, or the cube root, if you will, of b to the 5th. We have the square root of h cubed, and we have the 4th root of a c, and we are adding them all together. And the question was, well, it wasn't much of a question. The problem is stating, hey, get all of these under one radical. Well, that's weird, right? How the hell are we going to do that? We have a cube root, we have a square root, we have a 4th root. How the hell am I going to put those together? Well, the interesting thing is that we kind of do what we're used to backwards. So all of these problems over here had to do with having a fractional exponent and getting it into the root form. But in order to even pull this guy off, what we're going to have to do is go from the root form to a fractional exponent first. So let's do that. Now remember, the power is going to be the top part, the root is going to be the bottom part. So this b is going to be to the 5/3. The a is going to be to the, it helps if I write the a rather than just randomly, them neurons is misfiring already. Only an hour in. Ah, yeah. There's the letter A. I missed you, A. Okay, so we got a power of 3. The root is square, so that is 2. And then over here, we have a C. It doesn't have a power, but there's one of it. So it's going to be 1 over. Its root is 4. Now here's something interesting. If I was trying to put all of these under one root, what would have to happen? They'd all have to have the same denominator, right? Because if they all have the same denominator, then they would be under that root. So what you end up doing is you end up getting a common denominator between these 3 fractions, and then we don't simplify. So what we have is something that we are going to kind of work upwards towards. So we have a 3, a 2, and a 4. What's the first number that 3, 2, and 4 all go into? 12, right? 3 and 4 multiply together, we get a 12, and 2 goes into that, so we're peachy there, right? So what we're going to do, and you don't have to write this, I'm going to write this again, just so I have these 2 separate things in the notes. As 2 separate steps. Because I know this one could be a little confusing. But what we're going to do is we're going to multiply each of these fractions by whatever is going to make them have a denominator of 12. That one by 4 over 4, this one by 6 over 6, and this one by 3 over 3. So I end up with b, there we go, b to the 20 over 12 plus a to the 18 over 12 plus c to the 3 over 12. Now, I'm going to put another step here that follows one of those rules on one of the earlier slides, well, literally on the previous slide. This step is mostly unnecessary if you see where you're going to end up, but the next step is going to be something mainly for the notes, because this is technically what you're doing. You were looking at this and you were saying, hey, if all of these are over 12, then what you could do is pull out that fraction. Like so. You're saying, hey, they all have that common 12th. So that happens. There are 2 steps left. And the last one is purely because I felt like making this problem a little more complicated. So we have this whole thing to the 1/12th power. Guess what we're going to do now? This is the 12th root of that crap. B to the 20 plus A to the 18 plus C to the 3rd. Actually, no, because I forgot those are pluses between them. This is it. That's all I can do. That's it. 12th power, 12th root of that thing. What I wanted to do would have worked if I had multiplied them all together in the first place. But since I put pluses, I broke my intention. Isn't that nice? Don't we like that? I'm glad I didn't write number 5 on this page. Totally wouldn't have had space. Hold it there for a minute in case people are taking notes on the internet. I have no idea if you are. As I'm doing this, I am checking the weather report because I did ride my bike here. And I do hate the temperature outside. 34 feels like 30. Oh, that's gonna get worse in an hour and a half. Cool. No pun intended. It's perfect weather to bike downhill, right? That wind chill on my face is gonna feel great. Gonna feel great. Yes, I know I do it to myself, and yes, I do reserve the right to complain. I complain at all times. There is no exception. In fact, I complained about having to come here and teach you guys. So you guys can all feel free to complain about having to put up. That is out of focus. There we go. Yeah, what the heck did I have for number 5? Yeah, all right. I decided to only have one example like this, but usually when you learn these things, this particular problem, you would see an entire lesson planned around it, and you would end up having to do like 20 of these. So sometimes you will end up with a bunch of things with radicals added or subtracted together. And you'll always see that word right at the top, and it'll say simplify. Okay, so let's simplify this. Now that second one, that 6 cubed root of 3, I can't really do anything to that. You might look at this and you might say, oh, simplify. Maybe if I turn things back into fractional exponents, I can do something. Not really.
for the most part, when you do these types of problems, you want it in the radical form, and all you're really going to do is you're gonna take everything and you're just gonna see if you can simplify those radicals first, okay? So I can't do anything with the cube root of 3, right? That just is, that's just the cube root of 3. What I can do is simplify the cube root of 81. So 81, that's 9 times 9. And each of those 9s is a 3 and a 3. So we end up with 3 times 3 times 3 times 3. And it's the cube root of these. Well, cube roots mean anytime I have 3 of a factor, it's going to come out. Now I already have a 5 out here. So what am I going to do? Well, it gets multiplied. And then you have the cube root of whatever's left. Well, what's left? 3. Okay, well, if these are multiplied together, can I just multiply the 5 times 3? Yes, because if all of them are multiplied together, then you can absolutely multiply 2 of them together to simplify that a little bit. Oh, well, now these radicals are the same, right? I have 15 cube root of 3 minus 6 cube root of 3. So what you kind of do is you kind of end up treating these as like terms. Because, yeah, that's some weird funky number, but I got 15 of them here. And I'm taking away 6 of them here. So all you end up doing is doing 15 minus 6. That's a 9 cube root of 3. So you kind of just treat that cube root as something to be pushed together with like terms, right? Now, one thing I will say is that if you had a more complicated problem, there was like 8 of these guys all being added together. Sometimes you might end up with a cube root of 3. Sometimes you might end up with a cube root of 2. You can't put those together. We can't do what we did on the last problem and squish everything together. You can't just force all the terms together all the time. I mean, you kind of could, but you wouldn't want to, because if the idea is simplification, you want that cube root, those roots to be as small as possible. You're not trying to beef them up to get all under one weird squiggly root. It's good to not have a squiggly root, especially when it rains. So how are we feeling on this stuff? We like it, we don't like it, we hate it, we hate ourselves. Yeah. It's funky. Comes in handy. Here and there. Or would you ask for a
Question for really specific. Probably construction work or something.
usually I default to construction work. Everything has a physical application. But also not like if we're playing with exponents, you know, we think of things squaring as they go up. We think of things cubing as going up. But the real world doesn't always fit perfect integers. So it goes up at some weird freaking rate. And a lot of times those rates could be just fractions. We work with that, and then we can manipulate that the same way we can manipulate the nicer ones. Now, if it's some horrible thing that I can't represent as a fraction, I don't know what I do. If I can't represent it as a fraction, I haven't done a whole lot of problems where my exponent's a decimal. I haven't. I have done some. They follow the exact same rules. It's math. Everything follows the same rules.
There are no exceptions to any of the rules I've told you at any point, ever. It's like in English, when you learn I before E, except after C. And then there's like 40 minimum examples of, well, except for that. Again, English doesn't make sense. I'm very big on syntax and logic, and obviously that's where the math comes in. So you can see me hating language. Okay. So do we feel good about fractional exponents? Feel just as good as we did about what the heck a function is? Wait till you get these with variables in them. I actually don't know if we needed to do any examples of variables. For my own benefit, actually for you guys' benefit. Give me a second, give me a second. I have no idea what my password is. I'm not gonna lie. Why I have a password database on it. If anybody has trouble remembering your passwords, it's something called Bitwarden.
Oh, yeah.
I love it. I love it. Oh my God, that's totally the default password and I never changed it. I'm a terrible person. Yeah, sure, let's save the password. Get the hell off my screen. Oh my God, that was horrible. Oh, I am sorry to all of you. I don't care about anything this thing says. No. Ooh, that looks fun. That actually just looks like the last one we did. You would do the same thing and then multiply it by 10.
140.
Nah. That's what you would do right there, for anyone curious. Okay, no, I didn't need to have variables in any of these. Cool, that's good. That's good. That's good. Always sign out. I never sign up, I never log out. I just literally just close it. I've never logged in to that outside of my own home. Okay. Cool. Yeah, so we're good. That covers it. That covers our concepts. We're happy. Let's do more stuff. Let's do polynomials. Polynomials. Word polynomial is from the Greek words poly, meaning many, and Latin nomen, meaning name. So it just means many terms. I told you something earlier was a polynomial. Cool. That literally just meant it has more than one term. So you have special names for the first three. Monomials, one term. Binomials, two terms. Trinomials, three terms. Easy, right? Pretty basic. Past this, you just refer to them as polynomials. So you'll usually say polynomial of degree, whatever the heck your highest power is. And that's actually going to be one of the slides. So don't stress that concept too quickly right there. So terms in polynomials are separated by pluses and minuses. Why? Well,
That's kind of like the thing lowest on the chain of order of operations, right? The last thing you do is just put all your stuff together. You gotta multiply and divide and everything first, because those things are happening all together. And then at the end of them, you can kind of squish them together. So that's why it's all separated by pluses and minuses. It's easier to look at it that way. That way you can say, hey, no matter how complicated this polynomial is, you know, I could have AB over WQ, and they all have weird exponents. But as long as there's a plus after it, I'm like, cool, that's a term. It's a hideous term, but it's a term. So polynomial is defined as an expression which is composed of variables, constants, and exponents that are combined using mathematical operations such as addition, subtraction, multiplication, and division. And there is no division operation by a variable. So the constants are all just numbers. So all numbers are constants because the value of the individual numbers cannot change. So if you hear me refer to a constant, that just means, hey, it's a number. It's a number without a variable attached. So that's something that pretty much once you hit algebra, you'll see the word constant a lot. Just a number. Number isn't changing. Variables are any letter, and exponents are, you know, we just covered exponents. It could be whatever number you feel like. You can have algebraic exponents. I can have 5 to the A. It happens. It does. Those are logarithms. They're exponential in a different direction. It's great. I don't think we have to cover that at all. It's great. So easy way to look at that is saying, hey, if I went back to that 5x squared blah, blah, blah equation that I had on the earlier example slide. Well, you know what? We're on slide 14. Blah, 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 blah. Here? Yeah. If I look at that thing, I got 5x squared and a 2x and a 3. And they're all being added and subtracted together, right? Cool. Well, that means I have multiple terms. So this is a polynomial. I don't have any division of variables, so we're good. Now, we have a plus and we have a minus. Those are separating our terms. So the 5x squared is a term, the 2x is a term, and the 3 is a term. And I would look at that and say, that 3 right there is our constant term, because that 3 isn't changing. Whatever the hell I got to the left of it, cool. Plus 3. 3 more than all that. So that's literally what I'm talking about right now. I'm just defining things that we've already seen, even straight lines. That's a polynomial. 3x minus 2. It's 2 terms. If it has 2 terms, what is it? It's a binomial, because there's 2. This last one had 3 terms, so it's a trinomial, 3. If I have, if I just treated this as its own thing, that would be a monomial, because it's one thing. That's it. That's the concept I'm throwing at you right now. We're just naming, we're giving terms for what we've already played with, right? Now, why are we doing that? Because it has applications. I guess based on my on the definition, can't have that. There we go, good enough. So monomials are anything as simple as a number to anything horribly complicated with a bunch of variables on it, right? That's a monomial. Monomial. Now I'm not trusting myself on saying that out loud. So they're just a single term, right? Binomials are made of two terms. As stated before, they're just separated by pluses and minuses. So binomials are two monomials added or subtracted together. So a plus 2, that's one. XY plus x squared, that's another one. You could have a horrible, horrible string of variables multiplied together. But if there are a bunch of things just multiplied together, cool, that's a term. It's a ugly term, but it's a term. Now we get to degrees. So this is another conceptual thing. So the degree of a polynomial is defined as the highest exponent of a monomial within a polynomial. So that sounds weird, but it's literally basically saying, hey, the thing with the highest power. That's, so like that 5x squared, blah, blah, blah. The highest power on that thing, on any of those terms, was a 2, right? So that was a polynomial of degree 2. Because you just roll with the highest power. Now, I don't think this comes into play at this level, but I've had it in here because it's useful to know. Because when I first saw having to identify degrees with things that had multiple variables, I was like, wait, what the hell? And essentially what ends up happening is you have multiple variables multiplied together. The degree of that term is adding the exponents together. So if I have 2x cubed y squared, I would say, hey, that thing's got a 3, that thing's got a 2, the degree of this thing is 5. You're basically counting how many variables are there. I don't care what their names are. It's just, yeah, there's 5 variables there. So it's a degree 5. So as I have down here, you don't have to stress this too much. You kind of do it naturally. But when you're writing them out, it's always best practice to write them in descending order of degree. It's just easier to write, right? Like 5x squared, something x, and then some number. You write it on the way down in terms of powers, and it's easier to kind of wrap your head around. You got it in a weird jumble, it's kind of harder to wrap your head around. Not a whole lot past that, right? So this one, I literally just threw together. Okay, not so literal. I didn't physically throw a PowerPoint slide. I imagine I could do that if I saved it to a flash drive and threw it at someone's head. That would be literally throwing this together. Best idea I got. But yeah, we're just gonna eyeball this. None of this is gonna require us to write any of this down because it's just looking at it. Like number 1, how many terms are there? 2, right? So that makes it a binomial. What's the degree of this polynomial? What's the degree of this binomial? The highest power hanging out? The 2. So the degree is 2. That's it. Number 2, x plus 5. We got another binomial because it's 2 terms. What's the degree? Well, we don't have any exponents, but how many x's do I got right there? 1. So that's another useful thing to do. Let's state the degree on each term on this one. The x, it has 1. We have 1x, so its exponent would be 1. So the degree of this binomial in general would be 1, because the 5 doesn't have any exponents, right? In fact, how many, if I just had a 5, how many variables would that have? None, right? So the degree of 5 would be 0, because there aren't any. Number 3. Well, how many terms I got? 3? Okay, so it's a trinomial. Okay, what's the degree of this trinomial? Highest things there on the left, we got x to the 5th and y to the 3rd. That's a grand total of 8 variables, so the degree is 8. Cool, so trinomial of degree 8. That's all we need. Number 4, we have the number 141. That's a monomial. There's one thing there. What's its degree? 0. We don't have any variables. 0. And number 5, 3x to the 15th plus 2x to the 14th. Two terms, binomial. Highest degree, 15. Okay, there we go. It's a binomial of degree 15. Did I necessarily need this slide? But I figured it'd be good to be able to eyeball some of these and be able to understand what's happening there. Did I cover? Did not. Okay. One thing I do want to mention is another term that I apparently forgot to write down. And you'll see this term pretty regularly. Look at that. Look at the first one, 2x squared. Just look at that piece. That 2 we know is a constant, but in this particular case, it's not a constant term, right? It's just part of something. The term you would use for what that 2 is a coefficient. The coefficient of that term is 2. That's just a word you're going to see pretty regularly, and it's literally basically just saying, hey, what's the number on that term? The coefficient. Facts, in case people go back to this later. There we go. Number on any term of the variable is referred to as its coefficient. Okay. You feeling good about that? That's not bad, right? Okay. Let's look at multiplying these things. I love multiplying these things. It's not too bad. So to multiply two polynomials, you multiply each term in one polynomial by each term in the other polynomial, and then you add them together and simplify if needed. So in each multiplication, you start with the constants and multiply the variables together. So as you can tell, we're going to be working our way up in this particular lesson, starting off with just multiplying a single term by a single term. So what do we do with that? Well, my example is 3xy times 2x squared. What you end up doing is you just multiply the numbers together, you multiply the variables together. So you kind of smush the whole thing together, right? So you'd look at this and say, you don't have to write it out the way I did there. This is just to understand what's happening. But you can look at that and say, oh, I got what's happening. What I usually do is I start with the numbers and then I move on to each letter and I work my way down. So I would look at this and I would say, okay, 3 times 2, 6. Okay, first variable, x. I have an x times an x squared. Okay, what do I get? X cubed. Okay, then I have a y. Well, okay, I don't have anything else there, so I'm going to multiply a y on the end. So I get 6, x cubed, y. Not bad, right? And then, similar to how I had before, for easier organization, the variables are often written in alphabetical order. Now, I definitely had something in mind when I was thinking of that, because I have had, particularly in some really weird calculus problems, I have had some horrible doozies of insane amounts of X's and Y's, and they all have different powers. Like, oh, there's 7 X's on this, and 6 Y's on this one. There's 5 X's and 3 Y's, and there will be like 20 terms. And it's like, oh God, how do I put these together? Well, if you write them, because technically, I'm just gonna have it for the visual sake, I'm gonna delete this here in a second, but technically, this is equal to 6y x cubed, right? Because it's the same things, just multiplied together in a different order. You can see how if I had to add a bunch of things together and some of them had x cubed y and some of them had yx cubed, I would kind of get a little dizzy if I had a bunch of those. So if I write my variables in alphabetical order, I hate my life less. This lesson doesn't cause too much of a stir at this level, but that's mainly for later. You do harder problems, you do it this way, your life's gonna suck less. Hey, look, a bunch of examples. Oh my God, I love examples. Oh my God. I'm actually gonna finish the slideshow tonight. Got an hour. Got up to slide 26. Where are we? Slide 19. No, I'm probably not going to finish this slideshow tonight. That's okay. I planned on that. I actually expected it. We're right for several of these down. Yes, I'm going to be a jerk and do number 5 pretty much all at once. Always hated how they taught problems like number 5. Makes so much more sense if you just learn how to do it all at once. If I have a bunch of things multiplied together, it just works out nicely. Okay. Number 1. 2 times 3x. What is it?
6x.
6x. Yeah. Cool. Yeah, because you just multiply the numbers together. I have 2 3x's. Cool. So you get 6. Number 2, that one's a little weirder, right? And by weirder, I mean, I don't know what 6 times 14 is off the top of my head. 6 times 10 would be 60, 6 times 4 is 24, that'd be 84. And then y times y squared. Box, never remember. Okay, number 3. Got 10t squared times a negative 14t. Well, positive times a negative, negative. 10 times 14, love it, 140. T squared times t cubed. So negative 140 t cubed. That's kind of nice, just multiplying through that way, and just looking at little pieces of it at first, and then just cramming them all together, right? I'm not stressing, hey, this is a 10t squared and I'm multiplying it by a negative 14t. I'm not stressing that those guys are a little bit complicated. I'm just worried about the numbers and then worried about the letters. Nice and easy. So about this point, when I was writing these equations out, I was like, I'm throwing too many easy, curveballs. I'm throwing too many easy problems. Let's just make them ugly. That's what I like doing. Whenever I would tutor, but people learned very quickly not to say, hey, Ben, can you make up a problem for me? Because I will go out of my way to make it horrifying. Horrifying. I have made some really weird problems. Although I will admit there was one teacher who assigned something worse than I've ever done. I filled 3 whiteboards this size with one problem once in a freaking college algebra class. And I am offended that I ever had to do that. And it was not okay. And it was a test problem. It was a take-home test. That was the only time I was perfectly content helping people on a take-home test, because there was not a single student in there that was capable of it. And in fact, most of the tutors weren't capable of it. I was just like, you know what, this is a challenge, let's do it. And I did it once, and I took a picture and I printed it off, and I'm like, I'm never doing this again. You guys can look at this. I am not doing that again. I've never made up anything that horrible. So I got 4 things multiplied together here, right? Now, I can tell this g squared at the end isn't going to mesh too nicely with these h's, right? But it's still multiplied together, so its sign is going to play a part in this, right? So I have a positive times a negative, so we're already negative, times another positive, so we're still negative. But then I get this negative right here. So this is all negative times another negative. We end up with a positive answer. So I don't care if these guys necessarily mesh well together. They're all multiplied together. So that's where the signs are coming in. I have 2 of these terms are negative. So multiplying those together gets me a positive. Okay. Then I got a bunch of h's and some g's. Well, if I decided to do things in alphabetical order, g comes first, right? So g squared, because nothing's going to combine with it, right? If I had some other multiplied by g, I could do that. But this guy isn't playing with any of these powers. It's not playing with any of them because it's its own thing. Now the h's, yeah, we're going to need to deal with those, right? So I got 5 of them, 2 of them, and 7 of them. So we're just going to add all those together. 5 and 2 is 7. 7 and 7, 14. I got a total of 14 h's. That's it. That's not bad, right? That one wasn't bad. We're just putting these guys together and keeping track of our signs, right? Well, let's apply that concept, the concepts we did of, doing the numbers first and the letters for later. Let's take both of those concepts and put them together for this guy. Now, this one, there's a lot of different ways you could do it. A lot of them. But notice I gave myself that much room. Because we could do this. We could do this in one step. Because how many steps did we take here? 1. How many steps did we take here? 1. So if I got all these things multiplied together, what's happening? Well, all the numbers are multiplying together and all the letters are multiplying together, right? Cool. So, first of all, positive, 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 negative. I got an odd number of negatives. I have one negative. That's gonna make the whole freaking thing negative, right? Put your minus. All right. Look at all these numbers. I don't like them, right? But I know all of these numbers are gonna multiply together. I got a 2, a 2, a 5, and a 23. I'm not multiplying that 23 by all the other ones in my head, right? But the 2, and the 5, I can multiply those together in my head. 2 times 2 is 4. 4 times 5 is 20. So I have a 20 and a 23. Throw that at your calculator. 460. Now I could have done that in my head. 20 times 23. I could have done that in my head because I could have done 2 times 23 and added a 0. That would have worked. But worst case scenario, multiply all those numbers together. We end up with 460. Okay, cool. Again, we have a bunch of variables. Worry about them in alphabetical order. I don't care if I have an XY here. I don't care if I have an XY cubed here. I'm multiplying all these things together. So I'm going to start with the first letter, X. One of them, two of them, one of them. 1 plus 2 plus 1, 4. We have 4 X's total. Okay, how many Y's do I have total? 1 here, 3 here, so 4 again. Do I have any other variables? No. Do I have any numbers I didn't take into account? No. Cool. We did that big horrible multiplication all at once. One step. Now let's say I didn't want to do this in one step. What were my options? Well, I could have multiplied a few of these together. I could have multiplied these two together and then these two together, and then put those together in one multiplication as well. You could do that. You could multiply these two together, and then the third one, and then rope in the fourth one. You could do that. You could do this one times that one, and then that times that, and then that times that. It doesn't matter, because like that earlier property, AB is equal to BA. You got some stuff multiplied together, it's going to end up being the same thing. So why not just multiply all the numbers together? Boom. Multiply the letters together. Boom. We're good. It's cheap and it works. That is my favorite way of doing math. Just be cheap with it. It doesn't have to be done in like 20 different steps if I can do it in one. As you can imagine, when I was in middle school, high school, elementary school, I got yelled at a lot for not showing my work. All the time. Because I would do things in one step and I'd be like, but that's what it's going to be. No, you have to show it. But I did. That's my work right there. That's it. So this one, I just kind of felt like writing it that way. We have 8 times a bracketed stuff, which is 3C multiplied by a 2B. That's a B. Might be a U. I don't care what it is. I'm gonna go with a B. I'm gonna assume I typed a B. So you look at this, and normally you would think, okay, I would have to start my multiplication from here, multiply my way out, and then whatever I have here, and multiply by 8. And that's fine. You can absolutely do that. You can absolutely do that. I'm gonna, yeah, let's just do it that way. Why not? If I multiplied these two things together, 3 times 2, 6, and a C, and a V. Cool. Now I have an 8. 8 times 6. 48, C, and B. Cool, not bad. Took a couple of steps. No problem, right? Well, I wrote this problem out this way because I wanted to show you guys, hey, doesn't matter how I wrote it. This stuff's all just getting multiplied together, right? This multiplied onto this, which then multiplied onto this. I could very well have written this 8, 3, C, 2, B. I could have written it that way. I could have written this 8 times 3C in a parentheses times 2B in a parentheses. If all of this stuff is multiplying together, then it doesn't matter how I do it. I am always going to end up with 8 times 3 is 24, times 2 is 48, times a C, times a B. Doesn't matter. We could have done this one in one step as well. As long as we can recognize, hey, that property is coming into play here. I am going to multiply all this stuff together. Doesn't matter. All right. So how do we feel about this? Tolerably? Tolerably. Cool. Cool, cool, cool. Well, then let's make it worse. Multiplying monomials and binomials together. Monomials and binomials together. We hit share on that. That's cool. All right. Good reveal. Good reveal. Go away. Go away. Go away. Okay. So multiplying monomials and binomials together. So essentially, same idea, but you have to distribute. You use the distributive property. So our example here is 3x times a 5 plus y. You can't put that 5 and y together. They're not like terms, right? So you would do this problem and you would say, okay, well, I have to distribute. So the 3x is going to multiply onto the 5 and 3x is going to multiply onto the y, right? That's kind of what I have written here. I just kind of hate the way I wrote it because I couldn't do like the little line hopping from the 3x to the 5 and then the 3x to the y. But essentially you end up multiplying a monomial times a monomial and a monomial times a monomial, and you get 2 terms, right? And actually that's an interesting way of looking at it. And it has helped me in the past when I've had to do these really, really big, really, really big, really big. If I have 1 term times 2 terms, the amount of terms I'm going to get at the end is 1 times 2. If I have 1 term times 3 terms, the amount of terms I'm going to get at the end is 1 times 3. Now, sometimes they'll clean up and go together, and that's fine, and you end up with less terms, but initially, that's how many you're going to have. If I have 2 terms times 2 terms, I'm going to have 4 terms initially. That has saved my butt a few times, just wrapping my head around that. Because if I missed something, I wouldn't have the right amount of terms. So sometimes they're written the other way around, where you'll have the 1 term second at the end of a parentheses. First of all, I hate writing anything right after a parentheses, right? It just doesn't look right. I hate that. I hate it. But it does the same thing. It means this is multiplying onto this, so you still distribute. Again, AB is equal to BA. 2 things are multiplied together, cool. Doesn't matter what the order is. Ta-da! You like how I went to an equation editor for number 4 and then number 5 I just like I literally go to an equation editor, type it out so it looks all fancy. Right click the image, copy, go over here, paste, and then just shrink it. I don't know a good way to put in an equation directly into a slideshow. At least on Google Google Sheets, Google Slides. That's right, there's slides. All right, I'll write out the first couple. I'm writing out all of them. Incoming suspected spam caller. Oh yeah, let's have fun with it.
Yeah, so
Hello.
that voting crap thing going on, I have it too. It's crazy.
Yeah, that's me. I have already done that, and I do have to go because I am teaching a class right now. It's okay. Have a magical day. Oh man, that guy felt like a jerk. I love it. I don't know about you guys, but I am hating all the voter text messages and calls I'm getting. Particularly because I love messing with spam calls. So like I kind of feel bad for messing with those guys when they're doing the voter outreach thing. But I also don't because they're annoying me. And I don't know what's outweighing what. Because when I want to be a jerk, I can totally be a jerk. I live and breathe sarcasm. All right. I wrote all of them down. We're going to do all of them. One big burst. It's going to be great. It's going to be great. So when I know that most of you were not in my first class that I taught this fall, but when I teach the distributive property, I always say this is a hell of a lot easier to understand when we do the algebra of it. Because when you learn about the distributive property, you usually don't have an X here. You just have numbers. And then you're like, why can't I just put those numbers together? Well, at that time, you could. So it kind of made it stupid. But the concept was there purely for this, because I have 2 times this whole thing. So if I have 2 times that whole thing, that means I have 2 times that and 2 times that, right? So that's what's happening, and that's how I like to do it with a little line thing. So we have 2 times 3x first, okay? 6x. Okay, and then 2 times 5, 10. That's it. That's all we got to do. That's the core concept right there. Every single one of these problems is going to fit that concept right there. So it doesn't matter how complicated these problems get, that is what we're doing. We are multiplying a thing times each of those things. I don't care if the things get bigger. If the things get bigger, we just get bigger numbers. I have a negative 12 times a positive 8x. Notice that I stress those signs. Negative times a positive, negative. 12 times 8, I don't know, 96. And there's an X on that one. so we get the x, right? Okay, well, that was that one. Now we gotta do that one. -12 times a -13, that's going to be a positive
166.
56. I think. Yeah, I literally just did 12 times 12 in my head and added another 12. That's 100% of most of my mental math is literally, I memorized all the perfect squares and I just kind of tweak them from there. Not even gonna lie. Okay, what the hell did I just say? Oh yeah, it's 156. Okay. Ta-da. All right. Next one, we have that term on the end. So there's a couple of ways you could do these. If you're not comfortable with this, you can rewrite it and put the 1/7 x at the front, just like all the other problems. If you don't care, like I never care, just reach a little further. So I have 1/7 x times 28y. Okay, well, kind of funky, but what's 28 divided by 7? 4. And we have an x and we have a y multiplying together. Those don't go together too nicely. They just hang out. 4xy. Okay. And I have 1/7 times -3. Positive times a negative. So I'm going to have a minus here. 3 times 1/7. Okay, so if I have 3 1/7, that means I have 3 7ths, right? Cheap way to conceptualize that. I like it. And then we just have 1x hanging out as a variable multiplying in here. So there's our x. And that's it. I can't simplify anything. I can't break that fraction down. So we call it good there. Call it good. Now we got this thing. This first guy should remind you a lot of the first multiplication here, right? We have 1/9 x times 18x squared. So the 1/9 and the 18 will go together. What's 18 divided by 9? 2. Variable wise, I have an x times an x squared. Okay, that's 3 total x's. So x cubed. That's all well and good, but now what about that thing? 3 over x. What the hell do I do there? Now, I could explain it on how to do that all at once, but let's say I have no idea. I have no idea, and when I have no idea, what I usually end up doing is I end up writing it out as multiplication, and I think, okay, I'm gonna deal with this. I'm gonna deal with this maybe later, maybe now. I don't know. Let's deal with it. So right here, this thing is being multiplied by an x, right? But we're also dividing by an x. Well, if I'm multiplying and dividing by the same thing, they cancel out, right? This x is going to cancel this x. What does that make this guy? It's not 3 divided by anything anymore. The x's canceling turn into 1 space, right? That's what happens when you cancel. So it's a 3 over a 1, which is a 3. So I have 1/9 of 3. So that's 3/9. All right, well, I don't like writing 3/9. That reduces to 1/3. That one's a little funkier, right? But it works. It works. Look, it's the last one.
One question, just say that 1/9 was an x squared times the 3x, right? So it'd still
So
be
it'd
like,
be over a 3x.
yeah,
Okay, okay.
so
The question is basically, what the hell, right?
yeah,
Okay, that's fine. All right, well. These are all kind of multiplying together. So one way you could conceptualize this is by separating this thing out. A lot of people hate me when I do this, but you can look at this as being a 3 and a 1 over x. Right, so I got the number component of it and I got the variable component of it, right? Well, we know what the numbers end up being. End up with that 3/9, which breaks down. But what happens with the x's? Well, if I multiplied that, put it over a 1, multiplied it over, I'd have x squared over x. Well, we've done this, right? Top power minus the bottom power, you end up with 1. So we got 1/3 x. That's another way of looking at it, but it all ties back to the same concepts. Ties back. I got x squared, I'm dividing off one of the x's. There we go. If I had x to the 10th and I had it over x cubed, I'd be dividing off 3 of them, so I'd have 7 left. So those concepts, that's one thing I appreciated about tutoring. When we had an academic skills center and I was bouncing between a bunch of different people in a bunch of different classes, my brain went from, I learned this at the beginning of this class, and this in the middle of this class, and this at the end of this class, to all of it all at once. And that kind of clicked something in my brain, because suddenly I wasn't looking at things and I just have to keep this core concept right now, and this is when it applies, and I don't have to worry about that for a while. It all applies all the time. So the earlier concepts of dividing these fractions like this, jumping back, rolling up. What we just did is this guy right there, the upper right. And that concept will apply at all times on all math forever. So I don't have a nice way of giving you the experience that I got when I was tutoring, and that clicked in my head. I don't have a nice way of doing that. All I can really do is stress that all the concepts will apply all the time. So don't blindly forget a bunch of stuff thinking it's not important, because if I tell you, hey, these are rules, the rules themselves will always apply. The rules themselves will always apply. Because hey, Ben does love multiplying by fractions, right? Look at these fractions multiplying together on number 5. I have 1/2 times 2/5 y. 2/5 y. That could be written as a 2y over 5. I don't even care. But I have half of 2/5. I got half of 2 of something. That means I have 1 of something, right? I could write them down next to each other and multiply through and reduce. I could do that. I would have 2/10, which breaks down to 1/5. I could multiply them together and cancel out the 2's. That works too. But I particularly like my tried and true. Hey, what's half of that? I love having basic fractions and just being, not just saying, hey, what's half of that? Because I'll see people reach for the calculators on problems like this. And then if I just say, hey, stop it, what's half of that? It clicks. Like, oh, that's all I'm doing. Yeah, that's all you're doing. If I multiply that 1/2 over there, 14/6. Yeah, I could have reduced that. I don't care. What's half of that? What's half of 14? 7. Okay. That's it. What's half of that? It's a good concept to get down. Don't have to stress multiplying fractions all the time. If it's something basic and you can just say, hey, what's half of that? What's 1/9 of 18? It's 18 divided by 9, 2. Cool. Don't stress the fractions. Try to make them work for you. How do we feel about multiplying a monomial times a binomial? Be okay with it? Are we about as okay with it as we were multiplying a monomial times a monomial, but we're doing it twice per problem? That's literally all it was, right? How is it? Oh God, my back hurts. I'm not gonna lie, guys, my back really hurts. I got like 5 more slides to go.
I'm gonna make it, boss.
Huh?
I'm gonna make it.
I don't think I'm gonna make it. I'm not gonna lie. I think I need some rest. I think we're gonna call the class. Because I have 19 minutes to go. I really want to spend some time on this thing. Look at that thing. This isn't bad. It's really not. It's really not, but it's also something you're going to want to have memorized. It's called the FOIL method. But it's going to be multiplying a binomial times a binomial. And the way I like to teach this, the way I like to teach it is going to scale up. Here's a horrible preview. Look at number 5. Look at that thing. Holy Jeebus. There was no way we were gonna pull that off.
Trying to solve for the answer, correct?
Yeah, I couldn't cover all of this in the next 18, 19 minutes. So yeah, we're gonna round up to 8:15. I'm gonna call it good right now. I'm gonna go home, nice my back. Or I'm gonna use a heating pad on my back. I don't know, I kind of bounce between the two. I can't tell which one helps. I think they both do at different times. That's why icy hot's a thing, you know? Oh man, why do I not have any of that? Okay, well, it's freezing outside. I'm not back in the Walmart. Okay, so we're calling it good. You guys all have a wonderful night. On Tuesday, we are going to do a review of all of these particular things. We're gonna make some nice problems, gonna make some horrible problems. And then we will jump into binomials and higher stuff. And this nice blank one that here that says factoring, which is literally all of this multiplication but backwards. Great. It's also incredibly useful. Have a good night, everyone.
All right, Ben, you have a good night.
Tell me what to do. You're not my real mom.